So I will start with the review of the first lecture. If you remember, in the first lecture, we have done examples on entropy. And now I will continue with the examples on entropy, but now I'm going to talk about a different concept in entropy. But firstly, let me just have a small review. And if you remember, we have said that to find the entropy of pure substances, we have the two methods. One is that you have constant specific heats or the variable specific heats. If it is variable, you always go to tables. Okay. You have the formulas. For example, for ideal gases, you have the formulas. But even if you have the formula, at the end you have to go back to the tables to find the values that are required here. For example, this one is from the table, from table. Okay, so therefore, for example, this one is from table, from table. Okay. If it is variable specific heats, you have to use tables. Now for the constant specific heats, the formula is enough. You just use the formula and find the value of it. And also we have said that the non-conservation of entropy here, and because for the energy, we know that it is conserved. If you have a fixed amount of energy, that fixed amount of energy doesn't change, but it changes from one form to another. For example, if it was kinetic energy, then it becomes, here, if it was kinetic energy, then it may become the pressure energy. Or even if it is potential energy, then it may become internal energy. Okay, it changes in one form to another. But for the conservation of this one is for conservation of energy. But when we talk about the non-conservation of entropy, or in other words, we can say that the balance of entropy, in this case, the balance of entropy, you don't have a fixed amount of entropy because it may increase during the process. If you have started the process with entropy of, say that S is 7 at the beginning of the process, and during the process, this amount of entropy may increase to 9. Okay, so you will have two additional amount of entropy. It is from nowhere. Okay. It is added to the process, and we don't know where it comes from, but it comes from the process itself. Okay, so let me give you just one example. Say that I have an isolated system. So this one is isolated. Isolated system means that so inside that system, you don't have any energy transfer, so no energy transfer. And you don't also have any mass transfer, no mass transfer. Okay. So these two is not there. So if there is no energy transfer, if there is no any mass transfer, that means that there is no any transfer. So if there is no any transfer to the system, you will have, you expect that, so first the energy part and then the entropy part. If it is isolated system, if there is no any transfer, the energy of the system will be constant. It will not increase or it will not decrease. It will be constant. But when we say that energy at time t1 will be same as energy at time t2 if it is isolated system. Okay, but for the entropy part, if the entropy at the beginning of the process S at time t1, if it is in the amount of 7 at the beginning of the process, where you have the time t1, and if you take another time t2 and measure the entropy, it will be 9. Okay? And if you take another time, it will be 10. So it will not decrease, it will always increase. And you see that there is no any transfer, there is no any means for the entropy to increase, but it increases from the process itself inside the system, and therefore entropy is not constant. Okay? And the best isolated system to understand is our universe. Because if you take the boundaries of the universe very large, so that there is no energy transfer, and so there is no mass transfer, for our universe, the energy will be constant. Energy will not increase or decrease, but entropy will always increase. It will not be a constant quantity, because you have the entropy generation here, production. It is like a facility that produces entropy, and therefore the entropy doesn't have any fixed amount. Okay, this was from the previous lecture. Now I'm going to solve the examples. There is one more example here. So the example statement is we have a rigid tank. We will always use the previous tables, but for the next examples, the example that is here, we will use the different formula that I will talk about later. So first, this is the last example for the previous lecture formula, and then we'll talk about the new formula that will be required. We have a rigid tank filled with air of 5 kilograms and 5 bars, 227 degrees Celsius. So this is our rigid tank. Okay. Inside the rigid tank, you have the air, and it has a mass of 5 kilograms. It has a pressure of 5 bars. It has a temperature of 227 degrees Celsius. And it is well insulated. This part is also important. It is well insulated. For this well insulated system, this one is insulation. Okay, this is just an insulation around it. And the tank has a leak. So there is some part of the tank that there's a leakage here. So let me put this part. This one is the leak. So has a leak, and the air slowly escapes through that leak till the pressure is 1 bar. Okay, so the air slowly escapes. This one is very important part, and the pressure is 1 bar. So the pressure at second stage is 1 bar, and the process is very slow. So you should. And find the volume, find the temperature, and the remaining mass in the tank if air is ideal and escapes slowly through the leak. It reiterates the point here, which is the slowly part, because it will be required for our case. Okay, so this is the process, and these are the values that are given. Now we are going to solve it. Of course, the topic is entropy. We'll use the entropy balance for the system here and try to solve the values for the process. And for the second process, we only know the pressure. Okay, for the first process, if you remember the Gibbs phase rule, for the first process you have 2 values, for example pressure and the temperature. You can find any third value here, but for the second process we only have the pressure. We need one more property here. Okay, you need one more property because it is the Gibbs phase rule, if you remember, to find any third property. So in this case, we don't know the volume, we don't know the temperature and the remaining mass. Therefore, we need one more property. One more property, we will get it from this one will be entropy. So we will have the entropy. You will see how we will find it. We will have the pressure, 2 properties, and we can find any third property because it will be easy. At the end, it is Gibbs phase rule. It says that if you have 2 properties, you can find any third one. Now let's start. I will write the balance of entropy for the system, so that if you remember, if I go back to the equation here, it says that the in minus out plus the generated minus destroyed. Destroyed part for the entropy is 0, and you will have this equation. So now I'm going back to the case here. So our system, first let's select our control volume. Our control volume will be the air that is inside the tank. Okay, this is our control volume. CV is air that doesn't escape the tank. Okay, this will be our control volume, and if I write the entropy, you will have the change of entropy for our system. It will be equal to total in to the system, rate of it, total out from the system plus the generation term, it will be rate. And the inlet to the system, if you remember from our previous lecture, we have said that there can be 2 types. One is the mass flow rate, and the second one by the heat transfer. And for the work transfer, we don't have any entropy transfer. So for our case, for the system that's shown here, this one is a closed system. So why it is a closed system? So let me elaborate this point. This one is closed. So you have the leakage here, but we have selected the control volume, air that doesn't escape the tank. So in other words, what does it mean? That Let me talk about this one. So you have a tank here, and let's say that this is time at 0. So at the beginning of the time, you have the leakage, and so 5 kilograms of mass is inside it here because it is given in the question, and the sum of the air will leave the system. Okay, and when the process is ended, so T is end, you will have some air inside the system. You will have some of it. Okay, because here the pressure will be 1 atm, and the environment will be 1 atm, and the sum of the mass will remain inside the tank. Okay, it will not escape it. It will remain it. It will remain in the tank, and therefore, so that the mass or control volume, in our case, is the air that doesn't escape. Okay, or remains inside the tank when the process is finished. Okay. Write it. So it remains in the tank when the process is finished. Okay, this amount of air that remains in the tank when the process is finished is closed system. Okay, or I can give you one simple that analogy. Say that you will have so that this is the lecture, okay, and there are 5 persons inside the lecture. At T is 0, all of the people are here, but when the lecture finishes and the new lecture starts, okay, so that T is end, and the 2 people is always here. They don't leave the class. Okay, they are always here. If I select my control volume as these 2 people, if it is my control volume, this control volume will be closed because these 2 people are always inside the lecture room and till the end of the process. And even at the end of the process, these 2 people are inside the lecture room. And if I select my control volume as these 2 people, and then it will be closed system. Similarly here, I select my control volume such that the air inside the tank that doesn't leave the tank, okay, that always remains in the tank, and therefore it will be a closed system. So therefore the mass transfer, it will be 0. Now comes the heat transfer part, and for the question it says that it is well insulated, and therefore this part is also 0. And similarly for outlets, you will have the mass transfer, it will be 0, and you'll have the heat transfer, which will be 0. For outlets, it is also is there. So, and then comes the generation part. Here we have the generation part. For the generation part, so entropy generation, and if you remember, we have said at the first lecture, if the process is very slow process, and then for that very slow process, you will have the reversible case. Because if the process is very slow, it will be reversible. If it is reversible, this generation term is 0. Very slow process means that the time is very large, and therefore it will be approach. Okay, it will not be the exactly reversible part, but it will tend to reversible case, and then you will have the generation term as 0. In this case, where you have the third term as 0 and the first and the second terms are 0, you will have the change of entropy of the system. It will be 0. ds by dt of the system, and it will be 0. And if it is 0, you will have the S1, which is same as S2. Entropy at the beginning of the process is the same as entropy at the end of the process. So in that case, if I find the entropy at the beginning of the process, I can know that the entropy at the end of the process, and from that value, I can find any third property. Therefore, I need to find the S1, this one, at the beginning of the process. I need to find it. Then I can find any third property at the end of the process. But for this case, you can find the entropy. Find the entropy by using the constant CPCV. So you have 2 options. So one is constant CPCV, and the second option is that you can use the variable CPCV. And in the question, it states that you have a large amount in the pressure change. Therefore, we can take a variable CPCV, and we can find then the entropy. Now I will open the tables so you can see the tables, and I will go to the table for the air. Let me share it. Okay, for this table, so I will go to the table for air, and then from that air table, I will get the values for our problem. So let's go back to the air table. It should be 18, something like that. So this one is for ideal gas properties of air. And for the variable CPCV, we will need the PR, or the relative pressure values, and as well as the relative volume values. Just 1 minute. Okay, so at the beginning of the process, let me look at the value here. The temperature is 227 degrees Celsius. So if I convert it into the Kelvin scale, so because for the first stage I will need the temperature value. So it will be 500 Kelvin. So 500 Kelvin. So 1 minute, I will share both screens. So at the beginning of the process, the temperature is 500 Kelvin. And for the temperature value, you can see it here, ideal gas properties of air. So the temperature for 500 degrees Celsius, this is the line that we are going to look at it. You have the enthalpy value, we don't need the enthalpy, and we only need the PR value. You will see that. Why do we need the PR value? Because if I go back to the formula for the ideal gas properties, change of entropy, you can see if I need the constant specific heat, if I take this part, the constant specific heat values, you can just use the formula for the variable specific heats, which is the case for our problem. To find the entropy change or isentropic case, you need the PR values. You can see the PR value here. So you need the PR value here, you need the new R value. For our case, the pressures are given, therefore I will take the PR value. This is the relative pressure. Okay, it is exponential function, and it has been calculated at the tables. Okay, it doesn't have any physical meaning. It is just an exponential function. Okay, so we will take the PR values from the table for the first stage. Let me take it. For the first stage, the PR value is 8.411. So go back to our problem. For this one is T1, and for that T1 you have the PR1 value, which is 8.411. This is the first case. Now comes I know the T1, I know PR1. If you remember, for the isentropic case equation, isentropic means that entropy is constant. If I go back to the formula here, that you can see, P2 by P1 will be equal to PR2 by PR1. This will be the formula that we are going to use. We have the second pressure divided by the first pressure. It will be that second PR value and the first PR value. So for the first one, you have the value, which is 8.411. And for the first pressure value, it is given in the question, which is 5 bars. Since it is ratio, therefore I don't need to convert it. So this will have the same units. These will be cancelled out. So then for the P2 value, it is 1 bar. It's 1 bar. So then you can find that PR2 will be half of it. Half of the 8.411. It will be 4.205. This will be PR2 value. Now I will go back to the table again. So go back
teacher,
to the
what
table.
helpful?
From that table, from this PR2 value, I will find the entropy at point at stage 2. Let's go back to the table. So you can see the PR values here. For my second case, it will be 4.21. So it is 4.15 here and 4.52. And by using linear interpolation, you can find the temperature value here. So let's use that value. Okay. So go back to the PR value. Yes. You have the 4.15.3 here. And for next stage, we have the 4.915. This is the first one. For the first one, the temperature is 410. This is the temperature here. And for the second one, you have the temperature value, which is that 52. It should be 52. Let me correct it. For the second temperature value, it is 4.52. And then the temperature value will be somewhere around here, and it will be 410 Kelvin. And you will approximate that the change between this one and to that one is linear. This will have a linear change. And for that linear change, you will do just the interpolation here and find the value at the intermediate stage. But this one is the linear interpolation because you are interpolating between these. So this one is important, interpolating. If you extrapolate, you can find the values here. Okay, so then what I'm looking for is that the value, which is 4.20, somewhere around here. And find the value here. You can use just that 4.522 minus 4.513 divided by this one minus that one divided by the total. So now we are working with the extremes. Okay, this one is the slope of the line. That slope should be equal to 4.20. There is one more, 25. And the minus the initial one, which is 4.153, and divided by that the unknown temperature value here, which is T2 minus 410 Kelvin. Okay. This unknown is T2. If you solve this equation, you can find the value of the T2 here. Okay. But I will take the approximate value, and you can get the exact value by working out by yourself. And I will take the approximate value, which will be that it will be 400. So T2 approximate, okay. So 412 Kelvin. But you can work with the exact value here. This one you'll get the exact value. So with this PR2 value, I have got the final value of the temperature. I know it now. Now the question is, how can I find the volume and the final volume, and how can I find the remaining mass in the tank? And this will be the second part of the question. Okay. I'm sharing the screen now for the presentation only. Okay, to find since I know the PR2 value, or I know two properties at the end of the process. I know two properties. I can find any third one. I will use the ideal gas relationship. So ideal gas relationship says that P1 V1 will be equal to MRT1. This one is the ideal gas relationship. Similarly, you will have the P2 V2 will be equal to M2RT. And in our problem, we have said that it is closed system, therefore the mass remaining inside the system, I have a system that always includes the mass that didn't escape it. Okay. Therefore, let's solve the simplest one, which is the V1 is the same as the V2. So V1 is same as V2, and here, because it is rigid tank. Okay. Now comes the second part, which is the M2 and the M1. If I take the pressure value, which is the 5 bars here, so times 10 to the 5, it will be pascals, and the V1 value, so we have said it will cancel out. Let me first divide and then write it. So you will have the P1 by P2 will be equal to M1 by M2, and the R values are the same because it is the air, and the divide T1 by T2, and the P1 value will be equal to 5 bars. It's okay, no problem, and the P2 value will be equal to 1 bar, and the T1 value, which is given in the question, which is 500 Kelvin, and the T2 value, which is the value that I have found, which is 412 Kelvin. Now comes M1 and the M2. At the beginning of the process, the M1 value for this pressure and for this temperature was 5 kilograms at the beginning of the process. And at the end of the process, I'm going to find it. This one was the 5 kilograms. And the only unknown is here, M2. And from that value, you can find what is the value of the M2, and it will be 1.6 kilograms. If you work it out, you will get 1.6 kilograms. I have found the value for the second mass, and I know the temperature at the T2. Now comes the last point in the question, which is to find the final volume. Okay, this will be the last part, and the V2. And to find the final volume, I will again go back to the ideal gas equation, and the ideal gas equation says that, so you will have the V will be equal to mRT by the pressure. Okay. This one will be the ideal gas equation, and you can use either M1, R1, T1, P1, or R's actually are the same. You can use M2, R2, T2 by the pressure too. You can use any relationship to find the final volume, and if you use, for example, first one, and the M is 5 kilograms, R is for ideal gas, it is 287 joules by kilogram Kelvin, and the temperature 1 is 500 Kelvin, and the pressure 1 is at the beginning of the process, it is 5 bars, and to convert it in the SI unit, it will be 10 to the power of 5. Okay? Because you see it is joules, you cannot work with kilopascals, you should work with the Pascal units. And if you divide this ratio, you can work it out with the second one also. You will get 1.4 air curves. Okay, this is the end of the example. So what was the main part of the example? If I summarize it, the main part of the example was that it is very slow. Since it is very slow process, the generation term is 0. And the second thing about the process is that if I apply the conservation of the non-conservation of the entropy, I take my system or my control volume such that it includes the mass that is always inside the tank, that doesn't escape it. Okay, I've given a similarity here. Say that you have a lecture room with 5 persons at the beginning of the lecture, and if it is at the end of the lecture and the 3 of the person has left it, but 2 is always there, the same 2 people. If I select my control volume or the system as these 2 people, it will always be a closed system because these 2 people are inside the lecture room at the beginning of the process and till the end of the process. Okay, this was the thing that made the problem easier. Okay. If you have questions till now, you can ask. Otherwise, I'm moving on to the next example. Okay, so next example. Okay, the next example is that we have a 2 kilogram per second of steam that enters 3 megapascals of a reversible adiabatic turbine and exhausted in the two outflows. One outflow is at 100 degrees Celsius and 50 kilopascals, and 5% of this flow is diverted for home heating system at 500 kilopascals. And then the question says that determine the produced power of the turbine. Now let me first show how the turbine looks like. So we have a turbine in this way, and this turbine has inlet. So here, this one is the inlet, and from this inlet you will have which is the 2 kilograms per second. So this one is the inlet, which is 2 kilograms per second. And the question says that the exit is in two ways. You have one exit here. Let me put another exit here. So in one exit, 5% of this 2 kilograms per second leaves. In the second one, you have the 95% of this 2 kilograms per second. And then 5% of this flow is diverted for home heating system at 500 kilopascals. Now let me write the values that are given in the question. For the inlet, the pressure is 3 megapascals, and for the outlet, so we have for 95%, you have 100 degrees Celsius, it is given, and you have 50 kilopascals. Okay. And then 5% of the flow where it is diverted, the pressure is 500 kilopascals. You have 500 kilopascals. Okay. I have the values here. Now the question says that determine the produced power of the turbine. And I can write the conservation of energy.
Ben sual verebilirim.
Yes.
Ben bu 5%, 95%, yani 2 kilogram saniyede
yes.
2 kilogram. Onun 95% buradan kesir, 5% bu taraftan, o deməkdir.
Exactly, my friend. Okay, so the question says that determine the produced power of the turbine. So if I write first, let me write the conservation of energy. For the conservation of energy, if I take the steady system, if it is steady, then in should be total in to the system should be same as the total out. Okay, since it is open system, and for the thermodynamic problems, if you remember, kinetic and potential energies are most of the time neglected, and therefore you will have the enthalpy into the system with some mass flow rate should be equal to enthalpy out of the system. And you have two outlets, so that outlet 1 and this one should be 1, and the plus the outlet 2 with enthalpy 2. And also you have the energy transfers by the heat. The question says that it is adiabatic, and there is no need to consider the heat transfer. And since it is the turbine, you have the power produced by the turbine. Produced means that it is in the outlet part. It should be plus work outlet. Okay. The question says to find it. And the m dot inlet, it is 2 kilograms per second. Enthalpy at inlet, I know the pressure at inlet, which is 3 megapascals, but the problem is I don't know the second value for the inlet to find the enthalpy value. And if you remember Gibbs phase rule, and the Gibbs phase rule says that, I want to tell it again, you need to know two properties, and then you can find any third one. Okay. For inlet, you can see we only know the pressure. I don't know the second property to find the enthalpy. Okay, therefore I need one more property to find it. For the outlet, you have the first outlet. Say that this is the first one, out 1, and this one is the second outlet. For the first outlet, again, I have the values 500 kilopascals, and the m dot is 0.5%. It will be that 2 times 0.05. And the enthalpy value here, it is again unknown because it is 500 kilopascals, and I don't know the second property here. So it gives phase rule 2 properties, but I don't have any second property to find. But here you should remember that these 2 properties should be intensive. Okay, it should be intensive property. For example, if you know the volume here, it doesn't help. Volume is extensive property. If it is mass, it doesn't help. If it is, for example, so any extensive property will not help. We need 2 intensive properties to find any third one. Again, I cannot find the enthalpy at outlet 1. Now comes the mass flow rate at outlet 2, which is 95%. It will be 2 times 0.95. And the enthalpy at point 2, I can find it. You see, I know 2 values, which is the temperature and the pressure. So I can find it. And here, enthalpy will be found from 100 degrees Celsius and 50 kilopascals. And the work outlet, this is the question mark because the question itself says to find the work outlet. Okay, so you see there are 1, 2, 3 unknowns with 1 equation. Okay, it means that we need to have 1 more property that helps to determine all of this, and that property will come by the conservation of, so the balance of entropy. Entropy is not conserved. Therefore, when I say the conservation, it is wrong. The balance of entropy. Now let me write the balance of entropy. It says that, yes.
Adiabatik olduğuna göre siz neyi nəzərə almadınız?
Q, heat, istilik.
Ha, Q-dat olmaqda, çıxışda.
Bəli. So the balance of entropy says that the change of entropy of the system. So first of all, I should select my system here. This will be the system that I want to consider. And then this is the system, or CV. Change of entropy of the CV will be equal to the total in rate quantities minus total out in rate quantities plus the generation part. Okay, let's write it. Firstly, we will solve the first part. It is 0 because it is steady. Steady means that there is no change with respect to time. Okay. Now comes the in and out parts. For the in and out parts, if you remember, you can have the entropy transfer by the heat. You can have the entropy transfer by the mass. For energy, it is not the same. For energy, you have the mass, heat, and the work. So let me summarize it. It is the mass. It can be by heat, and it can be by work. But for the entropy, there is no work. Similarly, for outlet, you will have the Q dot entropy and the entropy by mass transfer. Mass can carry entropy, heat can carry entropy, but work doesn't carry entropy. And the generation part. With the given question, let's summarize what we have got here. This part is 0, and then comes the question says that it is adiabatic, therefore this term is 0. And this term is 0, it is adiabatic. And it is also says that it is reversible, and therefore the generation part is 0. Okay. You see, since it is that generation part is 0, now you have the inlet and the outlet are 0, you will have only entropy balance due to mass transfer. Now let's write it. So you will have the entropy with inlet S1. So you will have the, so let me erase it, so that you will have, for this question, you see that entropy by mass transfer, we should be same as entropy at in and out. So you will have the mass transfer entropy in should be equal to mass transfer entropy by out. Okay. And since the mass flow rate into the system, is equal to mass flow rate out of the system, since it is steady. Okay. Mass flow rates are the same. Okay. So, for example, here you have the 2 kilograms per second, but at outlets you have 5% and 95%. If you add them, you will have the 2 kilograms per second again. Okay. Therefore, these outlet parts are the same. Okay. And then you will have the entropy at inlet should be equal to entropy at outlet. Okay. So for this process that we consider here, the entropy is constant. So it is isentropic process. Okay. This one is isentropic process. So here you have the, for example, entropy at 1. That entropy will be same here. That entropy will be same here. Okay, you will have the same entropies at all different outlets, and this is isentropic process. Now to find if I know the entropy at 1, so what will happen is that for the inlet stage, I will know the pressure as well as entropy, and the Gibbs phase rule says that you can find any third one. Or for example, outlet, I know the pressure, and if I know the entropy, and I will find any third property. In our problem, it is enthalpy. And for the outlets, there is no any problem because I know two properties and I can find the entropy easily. Okay, now let's solve the problem and find the entropy values, and I will use the table. Okay. From these three outlets, where you have the same entropy here, and the same entropy here, at inlet, you cannot find entropy because you have one property. At outlet 1, you cannot find entropy because you have the one property, which is the pressure. But for the outlet 2, you have two properties, therefore you can find the entropy. Okay. From these two properties, I will find the entropy, and this entropy will be same as this through inlet and outlet. Okay, let me summarize it. So for inlet, so S1 can't be found. Okay, why it can't be found? Since we know one property, okay, which is the pressure. For outlet 1, again, it cannot be found because we know one property, which is pressure. But for outlet 2, so I can find the S1, okay, because I know since I know two properties. When I say that one property, it means intensive one property. Okay, should be careful here. So I know two intensive properties, and then from these two intensive properties, I can find the value of the entropy, so which is the pressure and the temperature. Okay, now let's solve it and find the value of find the values. Okay, let me now firstly open the table here. So I will share both screens with you. So, and then firstly, I will go back to the table. And now that I will use the table for the water, because the question is the steam, or therefore I will use the water table. And if you look at the final state, which is 100 degrees Celsius and the 50 kilopascals. Firstly, I should determine what is its state, if it is superheated, compressed, or saturated. So therefore, I go back to the saturated. Firstly, I should start with the saturated water, if you remember from thermodynamics 1. For the saturated table, you have the temperature as 100 degrees Celsius, but for that temperature, you need 101 kilopascals. And since the pressure given in the question is less than that one, so you see the pressure is less than that one, and then you will have the superheated. So let me write it here. So here you have the pressure is 50 kilopascal, and the temperature is 100 degrees Celsius. Okay. For these values, it is superheated. Okay. And the table I've used is A4. Okay. From A4, it is superheated. Now I'm going to superheated table and to find the values. So I will go back to superheated table. For superheated table, I will need 50 kilopascals, which is 0.05 megapascal. And then I will need the 100 degrees Celsius. So 100 degrees Celsius, this line, and for 50 kilopascals. And then you can see the entropy value at the fourth column here. You can see the entropy, and it is 7.6953. Okay. The entropy value is 7.69 at 53 is kilojoules per kilogram Kelvin. 6 point. Okay. This is the entropy for this stage. Okay. Now what happens is that I know this entropy for the inlet and the outlet 1. Therefore, since I know these two properties, I can find any third property. Okay. Now I've become this rule that I've written here. So now the H1 can be found. How can I find H1? I will find with the pressure at 1 and entropy at 1. I will find enthalpy at outlet 1, and how can I find it? I will find by, I know that the pressure outlet 1 and S1. You see, so I just know the value of the entropy and I will find the rest of the values. Now let's go back to the chart again. So first I will start from the inlet 1. For the inlet, the pressure is 3 megapascals. Okay, so let me go back to pressure table. And for saturated water, for 3 megapascals, you can say 3000 kilopascals. And the entropy is from 2 to 6. You can see the entropy range for 300 kilopascals. And in our question, entropy is 7 point something. You can see it is superheated. Okay, from 3000 kilopascals, entropy range, you can see it starts from 2 and ends at 6 point something. Okay, but in our case, the entropy is 7.7, therefore it is superheated. Okay, so from this one, superheated. Okay, I've determined it from A4. Yeah, from A4, I found it is superheated. Now I go back to the superheated table, and I will look for that 3,000 megapascals or 3,000 kilopascals. It is the table that I'm looking for. So this is the table, and I will need the entropy value, which is 7.69. You can see last column is entropy. It is 7.69. I don't have it. It is very good that I don't have it. So that, again, I will use the linear interpolation here. You can use the exact linear interpolation, but I will take the approximate values because I don't have time for the exact linear interpolation here. So then you will have the approximate value, H1 approximate will be equal to, for the entropy value of 7.695, then I will make it 7.70. 7.70. And if you look at here, it starts from 7.51 to 7.75. And for that one, you will have 1/4. Okay, then you will have the, now I'm looking for the enthalpy value. You can see the third column. This one is the enthalpy. So this one is enthalpy. You see, I'm looking for this column here. Okay. And I will determine the enthalpy values. Where is that? Yes, from this line here. You can see, I know that these two entropy values, from these two entropy values, I will determine the enthalpy value here. Okay. And since it is 7.70 and it makes almost 1/4, okay, then I will add that quantity over here. So it will be around, so 3,906 kilojoules per kilogram. Okay. This is approximately, okay, you can work the exact enthalpy value here. So this exact enthalpy value, it will be, let me show you how can you work out. It will be H and the S. So that when S is 7.5103, let me write it, it is 7.5103, and the enthalpy value is 33682.8. And when the entropy value is 7.7590, and you have the enthalpy values, which is 39, 12.2. This is the second one. So this one is for the second one. And what I'm trying to find is that I'm trying to find the entropy value for 7.6953. I'm working for entropy value at 7.6953. I want the enthalpy value for that one. So what I will do is that I will take the linear approximation between these two range. linearity, and I will find the enthalpy value here. Okay. So you can work with the linear interpolation, you can find it, or I've taken the approximate value for the inlet, and this is for the enthalpy at inlet. And similarly for the enthalpy at outlet, I will find it. So that enthalpy at outlet, I will again use the P outlet 1 and the S1, and the P outlet 1 pressure is 500 kilopascals. And let me go back to the A4 to find whether it is superheated or saturated. For 500 kilopascals, you can see the entropy is at the last column and it ends at 6.82. Therefore, it is superheated. So I go back to the superheated table. So our superheated table, then for 500 kilopascals, it makes 0.5 megapascal. And then for this pressure, you have the 500 kilopascal and the, 500 kilopascal is here. And the entropy value that I'm looking for is that 7.69. So again, you can see it is not here. So therefore, I need to interpolate it again. Okay, or you can use just the approximate value here. I will use the approximate value and to find the value of the enthalpy here. So for the H, which is H at 500 kilopascals and enthalpy at 7.6953, and you will get H approximate. Okay, approximately it will be so that it is 9, 6, and 16. It makes 1/3. Okay, then it will be, so it is, you will add the 120. So it will be 3. You will have the kilojoules per kilogram. This is for the approximately for the H outlet 1. Okay, so that you have found the H outlet 1, which is okay, and you know H outlet 2, and you have found H inlet. This is from, this one is the inlet. Okay, just I will replace the values back here, and then we will finish the example. It will be 3906. For outlet 1, it is at 3300, and for this part, we have used the table itself, and the table says that, let me find it from the table, it was 100 degrees Celsius and 50 kilopascals. 100 degrees Celsius and 50 kilopascals, it makes 0.05, and the enthalpy is this one. It is at 26782.5 kilojoules per kilogram. Okay. So you know all of the values here, you know all of it, and you can find the work dot out. Okay. You can find it by just knowing all of the values here. Okay. If you have a question about this one, you can ask me. Otherwise, I will stop the question here and stop the lecture as well.